Well, I would like to spend much of the rest of the period. In other words, so that's how it relates to the Laplace transform. That's how it comes out of the Laplace transform. Here's how to use it, calculate it either with the Laplace transform or directly from the integral. And of course, you'll solve problems, Laplace transform problems, differential equations using the convolution. But I have to tell you that most people, convolution is very important, and most people who use it don't use it in connection with the Laplace transform. They use it for its own sake. The first place I learned that, outside of MIT people use the convolution was actually from my daughter who, she's an environmental engineer, a consultant, environmental consultant. She does risk assessment and stuff like that. But anyway, she had this paper on acid rain she was trying to read for a client. And she said, it was something about calculating acid rain falls on soil, and then from there, the stuff leaches into a river, but things happen to it on the way. The soil combines with it in various ways, reduces the acidity, and things happen. Chemical reactions take place, blah, 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 blah. Anyway, she said, well, then they calculated in the end how much the river gets polluted, but she said, but it's a convolution. She said, what's a convolution? So I told her she was too young to learn about the convolution, and so I thought I'd better look it up first. I of course knew what the convolution was, but I was a little puzzled at that application of it. So I read the paper, it was interesting. And in thinking about it, then other people have come to me, some guy with a problem about they had drilled ice cores in the North Pole and from the radioactive carbon and so on, they were deducing various things about the climate, 60 billion years ago. And it was all convolution. He asked me if I could explain that to him. So I want to give you an all-purpose explanation. It's the simplest one I can think of, which will cover all the applications that I've seen so far in this direction. If you learn this, I think you'll be able to adapt it to almost anything else, because MIT students are very good at generalizing. They're not very good at particularizing. If I give you a general formula, almost nobody can boil it down what it says in this trivial case. But if I give you a simple case, most people I seem to be very good at saying, oh yeah, that would probably work. Something similar would work here and maybe there. Good. So let me give you a sort of an all-purpose thing, a simple all-purpose model which can be adapted, which is a very good way of thinking of the convolution, in my opinion. It's a problem of radioactive dumping. It's in the notes, by the way, so I'm just, if you want to take a chance and just listen to what I'm saying rather than scribbling everything down, maybe you'll be able to figure it out from the notes also. So the problem is, we have some factory or a nuclear plant or something like that. It's producing nuclear material, radioactive waste, not always at the same rate. And then it carts it and dumps it on a pile somewhere. So radioactive waste is dumped, and there's a dumping function. I'll call that f of t, the dump rate. That's the dumping rate. Let's say t is in years. You like to have units. And quantity, kilograms, I don't know, whatever you want. Now, what does the dumping rate mean? The dumping rate means that on the time axis, if I have two times which are close together, for example, 2 successive days, new midnight on 2 successive days, then there's a time interval between them. I'll call that delta t. To say the dumping rate is f of t means that the amount dumped in this time interval, in the time interval from ti to ti plus 1, is approximately, not exactly, because the dumping rate isn't even constant within this time interval, but it's approximately the dumping rate times the time. over which the dumping was taking place. That's what I mean by the dump rate. And it gets more and more accurate the smaller the time interval you take. Okay, now here's my problem. The problem is you start dumping at time t equals 0. At time t equal t, how much radioactive waste is in the pile? Now, what makes that problem slightly complicated is radioactive waste decays. If I put some at certain day and then go back several months later, and nothing's happened in between, I don't have the same amount that I dumped because a fraction of it decayed. I have less. And our answer to the problem must take account of, for each piece of waste, how long it has been in the pile, because that takes account of how long it had to decay and what it ends up as. So the calculation, the essential part of the calculation will be that if you have an initial amount of this substance and it decays for a time t, this is the amount left at time t. You know, this is the law of radioactive decay. You knew that coming into 1803. Although it's, of course, a simple differential equation which produces it, but I'll assume you simply know the answer. K depends on the material, so I'm going to assume that the nuclear plant dumps the same radioactive substance each time. It's only one substance I'm calculating, and K is it. So assume the K is fixed. I don't have to change from one K from one material to a K for another because it's mixing up the stuff. Just one material. Okay, and now let's calculate it. Here's the idea. I'll take the t-axis, but now I'm going to change its name to the u-axis. You'll see why in just a second. Starts at 0. I'm interested in what's happening at the time t. How much is left at time t? So I'm going to divide up the interval from 0 to t on this time axis into, well, here's u0, the starting point, u1, u2. Let's make this u1. Oh, curses. u1, u2, u3, and so on. Let's call this un. Or maybe un plus what? Well, it doesn't matter. Okay. Now, the amount so what I'm going to do is look at the amount, take a time interval from ui to ui plus 1. This is a time interval delta u. Divided up into equal time intervals. So the amount dumped in the time interval from ui to ui plus 1 is equal to approximately f of ui, the dumping function there, times delta u. We calculated that before. That's what the meaning of the dumping rate. By time t, how much has it decayed to? It has decayed. How much is left, in other words? Well, this is the starting amount. So the answer is going to be, it's f of ui times delta u times this factor, which tells how much it decayed. Now, so times. So this is the starting amount at time ui. That's what it was first dumped. And this is the amount that was dumped. Times, multiply that by e to the minus k times. Now, what should I put up in there? I have to put the length of time that it had to decay. What is the length of time that it had to decay? It was dumped at ui. I'm looking at time t. It decayed for the time length t minus ui. The length of time it had on the pile. So the stuff that was dumped in this time interval, at time t, when I come to look at it, this is how much of it is left. And now all I have to do is add up that quantity for this time, the stuff that was dumped in this time interval, plus the stuff dumped then, plus and so on, all the way up to the stuff that was dumped yesterday. And the answer will be, therefore, the total amount left at time t that is not yet decayed will be approximately, you add up the amount coming from the first time interval plus the amount coming and so on. So it will be f of ui, I'll save the delta u for the end, times e to the minus k times t minus ui times delta u. So these two parts represent the amount dumped, and this is the decay factor. And I add those up as I runs from, well, where did I start? From 1 to n, let's say. And now let delta t go to 0. In other words, make this more delta u go to 0. Make this more accurate by taking finer and finer subdivision. In other words, instead of looking every month to see how much was dumped, let's look every week, every day, and so on to make this calculation more accurate. And the answer is, this approaches the exact amount, which will be the integral. This sum is a Riemann sum. It approaches the integral from 0 to, well, I'm adding it up from u1 equals 0 to un equals t, the final value. So it will be the integral from the starting point to the ending point of f of u e to the minus k times t minus u du. That's the answer to the problem. It's given by this rather funny-looking integral, but from this point of view, it's entirely natural. It's a combination of the dumping function. This doesn't care what the material was. It only wants to know how much was put on every day. And this part, which doesn't care how much was put on each day, it just is an intrinsic constant of the material involving its decay rate. And this total thing represents the total amount, and that is, what is it? It's the convolution of f of t with what function? E to the minus kt. It's the convolution of the dumping function and the decay function. And the convolution is exactly the operation that you have to do that.